In this video, we'll talk about graphical sensitivity analysis. So what is sensitivity analysis? One of the implicit assumptions of linear programming is that all the parameters used in the models are known and certain. However, in reality, the parameters may change and nothing is really certain. So then the natural question is, how do the changes in LP parameters change the optimal solution? And the changes in LP parameters can be of different types. You can have a change in the objective function coefficients. You could have a change in the left-hand sides of the constraints or the right-hand sides of the constraints. So this is one important question. And then, assuming that we already solved the LP, then the question is, how much can we change the LP's parameters so that the current optimal basis remains optimal? So the optimal basis essentially determines which of the LP's constraints will be active at the optimal solution. And if it doesn't change, then computing the new optimal solution will be relatively easy, even if the solution itself does change. And therefore, we don't need to solve the LP from scratch if the changes do happen. In this video, we will illustrate the ideas of sensitivity analysis on two variable examples, which we can solve graphically. We will use the heavenly pouch example that we talked about previously. So this plot shows the feasible region for that example, and this is our model. All right, and the questions that we are going to focus on are: how would changes in the problem's objective function coefficients or the constraints right-hand sides change the optimal solution? And the second question, will the optimal basis change if we have certain changes in the model's parameters? Alright, so we are going to start with changing the objective function coefficient. So we'll look at one coefficient at a time. So the optimal solution of the LP once again is shown on this plot. So we see that the optimal point C is located on the intersection of two of the defining lines for our feasible region, which are the second constraint and the third constraint. These are shown in red on this plot, and the optimal point is C, and we also have the isoprofit line that passes through the optimal point shown in green on this plot. Now let's look at what happens if I change the objective function coefficient of the first variable from 15 to some other value, 15 plus delta, let's say. So our objective is given by 15x1 plus 25x2, and we are going to change it to 15 plus delta x1 plus 25x2. Physically, this corresponds to increasing the profit obtained from one irreversible carrier by delta dollars. So when we express x2 through x1 from this expression, so now our z is given by this here. So x2 is z divided by 25 minus 15 plus delta over 25 times x1. So we see that the slope of our line is given by 15 plus delta over 25 now. So it used to be 15 over 25 or 3/5 before we made the change. So now it's going to be 15 plus delta over 25. And the slope of the isoprofit line is important in determining the optimal solution. So if the slope changes too much, then the optimal solution will move to another point, right? Since the only change we apply in this problem is the coefficient for x1 in the objective, the feasible region remains the same as before, but because the slope of the isoprofit line is now different, the optimal solution can change. So then the question is, can we determine the range of delta such that the optimal solution is still located at the point C here? Now, looking at the plot, we can observe that the reason why the point C is optimal is because this green isoprofit line is located within the cone created by these two red lines. Alright, so the two red lines, they define this region right here. And the fact that the isoprofit line is within the cone defined by these two constraints is what determines the optimality of this point C. Now, when we make the change to the objective function coefficient, we see that the slope changes, right? And the way it's going to reflect on the isoprofit line passing through the point C, it will correspond to rotation of this line around the point C. Also, the fact that the isoprofit line belongs to the cone defined by the two binding constraints at the point C means that the slope of this line is sandwiched between the slopes of these two lines. Okay, so for the third constraint, the slope is negative 4/5, and for the second constraint, the slope is 0. And clearly the slope of the isoprofit line, which is given by negative 3/5, is between the negative 4/5 and 0. And as long as the slope of the isoprofit line is sandwiched between these two slopes here, we will still have the optimal point at C. So let's look at what is happening when we slightly change the slope of this line. So making it a little bit steeper, we increase the slope in the absolute value and make it more negative. So this corresponds to an increase in the value of delta from 0 to a positive value. So let's say if the slope is like this, then let's see if the point C still remains optimal. So here we can see that now when the slope exceeds negative 4/5 in absolute value, so this line is steeper than the third constraint, then we can see that C is no longer optimal because there is some space for us to still move within the feasible region. So we see that there is some space to move around the point D, and if we move the isoprofit line a little higher, then it no longer passes through C, but it still passes through D, and clearly the point D is the optimal solution now. So in this case we changed the slope a little too much for the point C to remain optimal. On the other hand, if the change is not so dramatic, then we can see that the point C will still remain optimal. So again, as long as we stay within this cone defined by the red lines, the point C will remain optimal. So next we are going to compute the range of values for delta such that the point C is still going to remain optimal. We said that in order for the point C to remain optimal, we need to ensure that the slope of our isoprofit line is sandwiched between the slopes of the two red lines. So our slope is negative 15 plus delta over 25. And we need to make sure that we are between the two slopes that we were talking about. So for the third constraint, the slope was negative 4/5. And for the second constraint, it's going to be 0. So we need to make sure that negative 15 plus delta over 25 is between these two values. In order to determine the range of values for delta, now what we need to do is to solve this system of inequalities. So we have two inequalities, right? Multiplying both sides of the left inequality by 25, we will obtain minus 20 is less than or equal to minus 15 minus delta, which is equivalent to delta being less than or equal to 5. Alright, so now looking at the right inequality, we have negative 15 minus delta is less than or equal to 0, which is equivalent to saying that delta is greater than or equal to negative 15. So we see that for delta between negative 15 and 5, the point C will remain optimal. Once we are outside of this range, the optimal point will move to another corner. We already saw that if delta is slightly greater than 5, then the optimal point is going to move from C to D. And then if we keep increasing the value of delta, then eventually the optimal solution is going to move to the point E. For example, if my isoprofit line is this steep, then the optimal solution is gonna move to E, right? Now, if delta is negative and it exceeds 15 in magnitude, then what will happen? The coefficient for x1 is 15 plus delta, so it's going to become less than 0, and the slope is gonna change to positive. So, and when the slope of the isoprofit line is positive, we'll have something like this. And when we keep increasing the profit level, we see that the optimal solution is gonna be at the point B now. All right. So we determined that the range of delta such that the current optimal solution still remains optimal is between negative 15 and 5. And the way it reflects on the coefficient of the first variable in the objective, since it is given by 15 plus delta, this means that whenever C1 is between 0 and 20, we are still going to have the optimal solution at the point C. So this completes the analysis of this case.